J'ai le plaisir de vous retrouver pour cette troisième session de cette grande journée responsable du Technion France, un monde en transition, santé, durabilité, finances responsables. La troisième partie s'intitule « En route vers une médecine intelligente et équitable ». Assistée de l'intelligence artificielle et des technologies, la santé est en pleine mutation. La crise du Covid remet au devant de la scène les défis cruciaux à relever. La recherche médicale connaît ses limites. Certaines des avancées médicales récentes sont révolutionnaires. Les questions de l'accès à la santé pour tous et de la responsabilisation du patient ont refait surface et sont l'un des enjeux de cette évolution. L'IA est au cœur de la médecine du futur, avec les opérations assistées, le suivi des patients à distance, les prothèses intelligentes, les traitements personnalisés grâce au recoupement des datas, etc. Elle permettra d'améliorer la qualité des soins. On parle de médecine 4.0. Dans cette partie, des avancées scientifiques remarquables sont présentées, françaises bien entendu, et issues des labos du Technion. Ce qui nous intéresse ici, bien entendu, c'est l'impact social de cette médecine intelligente. Cette nouvelle médecine assistée de la machine pose des questions d'ordre déontologique, technologique, économique, social et remet au devant de la scène la relation médecin-patient. Alors, pour présenter cette partie avec moi, j'ai le plaisir d'accueillir Elsie Boglioli, fondatrice de BioUp, une structure qui accompagne les dirigeants d'entreprises du monde de la health tech, qui a pour ambition de créer de vrais leaders français dans ce domaine. Elsie est aussi au conseil d'administration de plusieurs entreprises innovantes dans le domaine de la santé et connaît donc particulièrement bien ce secteur.
Merci Valérie. Effectivement, je connais bien ce secteur, un secteur qui est clé d'un point de vue société, d'un point de vue éthique, qui est clé pour les patients, qui est clé pour notre qualité de vie. Et pourtant, on aura l'occasion d'y revenir avec certains des intervenants. Aujourd'hui en France, on n'est pas tout à fait à la pointe de l'innovation de cette révolution. Surtout, on n'a pas créé pour le moment de grands leaders qui soient reconnus au niveau international ou même au niveau européen. Alors, comment y remédier? Ça fait partie des thèmes qu'on pourra traiter au travers de certaines interventions. Évidemment, tout commence par de la science, par la bonne science et la recherche qui peut ensuite se traduire par des sociétés innovantes. Et on va parler, je pense, pour démarrer, de chirurgie de pointe et innovante. C'est bien ça?
Oui, avec Alon, mais pas seulement, de scanners sans radiation et de mains articulées. Alon Wolf est le vice-président du Technion, en charge des relations extérieures et du développement des ressources. Il est professeur d'ingénierie mécanique et biomédicale. Alon va revenir sur un des axes stratégiques majeurs au Technion dont je vous ai parlé un peu plus tôt, la santé humaine, Human Health, et nous présenter certaines de ces initiatives dans le cadre de cet axe-là. Donc, il nous parlera de prothèses de main 3D articulées, également de diagnostic au scanner sans radiation pour les enfants. Nous allons lancer une vidéo de présentation et Alon sera ensuite en live avec nous pour répondre à vos questions. N'oubliez pas que vous pouvez poser vos questions sur le côté droit de votre écran. À tout de suite.
Hello everyone, my name is Alon Wolf. I'm a professor of mechanical and biomedical engineering and the Vice President for External Relations and Resource Development of the Technion. In my talk today, I'm going to review one of my activities related to the Technion Human Health Initiative. To be more specific about social impact of this program out of the Technion. I'll talk about articulated hands for 3D printing prosthetic hands for children, and a little bit I'll touch about our method how to scan and diagnose scoliosis in children without radiation. As you may have known or may have heard, Technion has launched in the last year 3 major programs challenging the 21st century's challenges of humankind. One of them is the Technion Human Health Initiative. The second one is about advanced manufacturing, and the third about energy and sustainability. My work is actually going to be under the first initiative, the Technion Human Health Initiative. The motivation of this initiative is to try to put researchers together in a center where their different disciplines would meet And from these meetings and these interactions, new and exciting research collaborations are going to emerge, and new and exciting challenges are going to be solved by a group and combination of researchers, students, educational programs, and outreach activities. Well, the system or the Human Health Initiative is, if you imagine as a, as a temple or as a structure, then the pillars of these structures are the challenges, the specific challenges of human health, such as cancer, cardiology, aging, diabetics, etc., where the horizontals are the specific disciplines of the Technion researchers, where the meetings between the columns and the horizontals and the verticals are going to create these exciting collaborations. For example, if we take researchers from sensors, robotics, and tissue engineering, if they meet together and collaborate in order to solve something related to trauma or aging, etc. So this is what we're trying to put together, and we're in the process of establish this initiative. The main activities of this initiative is going to be around industry, NGOs, hospitals, and funding agencies, where in the center is the Technion Human Health Initiative. So it's going to be one big collaboration between resources within campus and external to campus, and the effect is going to be, as we hope, dramatic. In this sense, the Technion is very unique in its structure as a technical university with engineering and sciences departments and a medical school. So this will give us the framework to bring Technion, or technology that will develop under the THHI, the Technion Human Health Initiative, all the way from bench to bedside. In other words, from the lab all the way to the patient. My work in my lab, the BRML, the Biorobotics and Biomechanics lab, is mainly focused on theoretical kinematics, on robotics with emphasis on search and rescue, medical robotics, medical technologies, snake robotics, human gait analysis, with the emphasis on the large joints, knees and hips, scoliosis, lower back, Olympic sport research. In the last 2.5 years, we are serving as the Israeli Center for Olympic Sport Research. It's a collaboration between Technion and the Israeli Olympic Committee. And my talk today will focus also on the human hand, or the helping hand project, our outreach activity to the community. Well, Helping Hand gives the world a helping hand. It's a collaboration with Haifa 3D, an NGO from Haifa, where we actually develop low-cost prosthetic hands and give it out for children, whether in Israel or around the world. When you look about prosthetic hands, you can see in the market two types. One is the mechanical or the body-powered simple prosthetic hands, as you can see here, or the electronics, the mechatronics, the more robotic prosthetic hands. There are advantages and disadvantages to each, but in the last, I would say, 10 years, there is a trend to move from body-powered, simple hook-like prosthetic hands to something that looks more robotics, more natural, more natural to the user to use with fingers, almost like a hand that he or she either don't have or lost during an accident or something like this. There are already prosthetic hands available in the market, so we're not inventing the wheel here, but I want you to pay attention to the price tag. The price tag of the existing system in the market is in tens of thousands of dollars, which means that these systems are, of course, very expensive and not, I would say, not accessible by many people, especially not children that grow up of these limbs pretty fast, and the cost would be dramatic. So this is where we are stepping in this gap between something which is usable, friendly, and also low cost, not in the range of tens of thousands of dollars, but something like hundreds of dollars. In the work we are doing, we're trying to span the spectrum of the process from the data collection of the residual limb, developing algorithm to help the designer to design a prosthetic which is specifically designed for the user, a specific user or patient specific, then automatic adjustment of our designs to the user, and of course, at the end of the day, assembling it and giving it away to the users. By the way, the entire process here is available online, so everyone can log into our web pages and get all the tools that were developed for the data collection, for the design, and also for the assembly. Everything is available, and this is part of our philosophy that we either give those hands or we share the knowledge that we've created with others who would like to join this wonderful project. For the first phase that I've presented, what we did is quite a large study about human hand biomechanics, where we took users into a specific our gate lab or our motion capture system lab in order to analyze how hands grip and hold and manipulate objects. This work actually resulted with hundreds of samples of people grasping objects, and with using kinematic algorithms and other tools, we're now able to design better our hands. The second tools that we've developed through this project is a low-cost scanner to enable the users around the world and us also to scan and get a CAD model, something that we can work with, of the residual limb of the child or the adults that we're going to design a specific hand for. So this is a low-cost device, as you can see, made of wood. All the equipment here is available online, so you can buy it or you can assemble it according to the instructions that we're giving. The algorithms that convert the data taken by the cameras into a model that a computer can work was designed in a mechanical engineering CAD lab, and everything, as I said, available online. Then the third phase, as was stated in the pipeline, the parametric CAD design. So the hands are parametric, which means that all we need is one or two measurements of the child or the adult's hand, and our models will then adjust their size and adapt to the user, the specific user, so it's comfortable and proportional to the other side. Interface: the hands are either mechanical operated or electronically operated. As you can see here, we're using different kind of sensors like electromyography and ultrasound. Here you can see the electromyography available sensors and electronics. Everything is designed and tailored to operate the hands, and again shared by everyone on our website. The last thing I want to point on is how to operate the hand. So it turns out that to operate a bionic or a mechatronic hand is not that intuitive. It's not like us human, when we talk, when we just grasp something, we do it quite naturally. With a prosthetic hand, the user have to think. There is a psychological effect that the user have to think about what he's going to do. He's going to grasp something, so he needs to reach, then adjust the robotic hand, then grasp it, etc. So we want to take this burden away from the user and make things more automatic. So this was another work done in my lab from one of our graduate students. Try to automate the process and produce a cognitive or reduce the cognitive burden from the user, where the hand actually understands what the user is going to do and what the user wants to grasp and prepare itself, rather than have the user do it manually. And here you can see one of my graduate students, Journée Polinsky, demonstrating. So she's wearing the method. So she's wearing a set of sensors on her arm, things that could then be embedded in the clothes. And these sensors sense the motions that she's doing, and using deep learning and AI algorithm, you're going to realize now or see how the system works. Please pay attention to the hand. The hand is grasping only when she's doing a motion that is related to grasping. So she wants to grasp the cup. The hands or the sensors sense this, and the hands responds immediately. In a minute, she's going to present how she's doing other motions not related to grasping, and pay attention, like right now, the hand doesn't respond. This algorithm also would lower the psychological burden of the user, so they can be in an environment with other people, so they can move their hands, etc. And the hand will not just operate itself where there is no need for a grasp, as you can see here. After we develop all these tools, the output is a package that includes the design, 3D printing, the electronics, the algorithm, the software. Everything is packed under one umbrella, and then can be handled or can be given to a specific user or shared on the internet. And then the assembling process starts, assembling the hand and giving it away. Before we give the hand away, we test it quite thoroughly. And even with using it with the robotic system that we have in the lab, you see the robot hand effector here is one of the hands that we developed. And the hand is picking up an egg here from point A to point B. By the way, pay attention that it doesn't crush the egg because it senses. There are sensors in the hand that allows it to control the force that we apply on the environment. And here you see several samples of how we check the system on different scenarios that are dictated to us by the users. So some users say that it's more important for me to hold a tennis record. Some other purposes that he or she wants to use the robotic hand. So the robotic hand is adjusted to the specific task given to us by the user. And then after it's tested, validated, everything is okay, we're ready to give it away. And here you go. This is one of the first hands we gave in the UK to a British child, and you can see him already using the hand right after receiving the hand. Another hand, this is Daniel's hand in Brazil, again given, and also take a look at the design that we can, the design can be also tailored to the user, the colors or even a logo or whatever the user wants to have on the hand. This is Zach's hands from the United States. Again, right after receiving the hand, he can operate it and work. And the last example I want to show you is Ben's hand. Ben was wounded during the military service. He lost his hand. He's now using one of our most advanced mechatronic hand, and you can see him here holding a plastic cup without even crushing it and drinking using our prosthetic hands. And many, many more examples. So the hands is given away for around the world and shared. And here, down here, you can see the web page where you can actually download the drawings and the software and all the instruction how to put this hand together if you want to open activity in your community. I want to move to another project that is related to impact on society, and it's related to measurements of and diagnostic of scoliosis in children without the use of radiation. One of the main risk in treating scoliosis in children, as you can see here, is the extra exposure to radiation during treatment, and doctors usually wants to perform an X-ray on every visit, during every visit for the child, to try to see what is the dynamic of the disease. Scoliosis is a deformation of the spine, as you can see here. What we came up with is, instead of using X-rays, we want to use 3D cameras like the one here you see here that was actually developed at the Technion by Professor Ronnie Kimmel from computer science, and now been commercialized by Intel, was licensed from the Technion. And by using 3D cameras, not X-rays, we want to reduce the risk of children to be exposed too much to radiation and reduce the risk for cancer. The way we do it is we actually take the 3D camera and create some kind of a topological map of the child's back because we get a 3D image of the spine or the back, and by using again AI and deep learning, then correlate what we see from the outside to what is happening inside, or the 3D shape of the spine itself. During examination, the user or the patient is asked to bend forward and lean, and the camera is taking constant pictures. And at the end of the process, as I said, by using deep learning and AI, we are generating from a 3D image of the back, a 3D reconstruction of the internal spine of the child or the adult that we are diagnostic, a 3D curve that helps the doctor analyze the severity of the disease and the deformation and the dynamic of the deformation, again, radiation free. At the end of the process, we get medical data that is meaningful to the doctors. This is a collaboration that the Technion now has with HSS, the Hospital for Special Surgery in New York, and where we're collecting and creating a very large database that enables us to do this process very accurately and clinically significant. These are two examples of activities that came out of the Technion and are as part of the THHI and with social impact. We see and we expect many more activities like this to happen now with this new collaboration, a new dynamic environment between researchers from medical schools, engineering, exact science, and life sciences. But this, all these efforts cannot be achieved by a single researchers, and that is, I want to thank my graduate students, my PhD students throughout the years that were part of these exciting projects. Thank you.
Hi, Alon.
Hi,
dear
hi,
Alon.
how are you?
Nice
Hi,
to
Valerie.
see you.
Hello from Haifa.
Thank you very much for this brilliant presentation. That was really amazing, very clear. Thank you for that, for showing us what is the importance of the human health for the Technion. So we have one question for you, and this is one for...
Hi, Alon. Thank you again for your presentation. So we have a question from the audience, which is actually pretty broad. So I hope you can maybe give us multiple perspectives. So what is the overall vision of the Technion regarding social impact and industry?
Oh, actually, this is a very timely and very important question. So this administration put as one of the main target for its activity is to further and even better the relationship between, or the connection between the Technion and the industrial ecosystem around in Israel and around the world. And we truly believe that there needs to be an ecosystem between industry and academia, and one cannot exist. They need to coexist together, or one cannot exist without the other. Now, for the industry to be strong, vital, and relevant, it will need to have strong connections with the academia for R&D and to get all the new technologies and the new science to be implemented, so this industry becomes a leader in its field rather than a follower. Now, for the academia to be relevant, it needs a very strong and developed industry around it, surrounding it, first for the R&D relationship, and then for the students to have jobs. Now, you could see a very strong collaborations in departments when there is a well-developed industry around. You see a lot of students applying, very strong students, because they know that they have a horizon, they have jobs with high salaries. And in these cases, in those cases where the industry is less developed, you see less students applying to these departments. So there has to be a very strong ecosystem. Now, within this philosophy, we've put a lot of efforts in developing, or even further develop, not that we didn't have, but even further developing and simplifying all the processes of building those bridges between industry and the Technion. When I say bridges, I mean IP, and all this becomes transparent almost, how to bring information, bring knowledge, or take out knowledge. Everything becomes very simple, very clear, by very regular standards. And this takes a lot of attention from us as an administration. Actually, I happen to be responsible for this effort within the administration. And I don't know if you followed, but about 2 weeks ago, we signed a very important agreement with a very big corporate called PTC from America that came into campus, moved their R&D center to the Technion, inside the Technion with 100. It's a 6,000 people corporate. It's in America, but all their R&D in Israel is now moving into campus. And we're creating this very dynamic environment where students, postdocs, researchers can work with and in and out from this company. By the way, they are one of the major companies in I4, Industry 4. So very relevant question, and we're expecting many more corporates, many other companies coming now into campus.
Thanks for that. And I think actually this notion of ecosystem, when we introduced the session, we were just talking about the difficulty and the importance of creating leading companies for the jobs, for the students, and to actually make research available to patients. And I think this notion of creating a tight ecosystem is absolutely critical. And we'll get back to it in a moment because our next speaker will also be talking about that. Before that, maybe we have another question.
By the way, we like to see it as we like to see it as a spiral, or a vortex that gets bigger and bigger. One process feeds the other, and then it becomes larger. So a smarter industry needs smarter and more brilliant students. Then they need better universities. So there is a spiral kind of process with what we call in engineering a positive feedback that grows and feeds itself. Kind of, we feed them with technology and students. They require students. They need the technology. So this is the ecosystem I was referring to.
I couldn't agree more, and I think we have Florence, who will be joining us later, who probably agrees too. And I think indeed having successful companies is also what motivates students, and it's also what allows you to attract the best students internationally and not only locally. So I really could not agree more. Valérie, do we have time for a second question?
Yes, we do.
Completely different topic. Go ahead.
Okay, let's go ahead.
This is from Charles Nachmanovici, who apparently knows you and says, happy to see you. What about the artificial hand as children are growing? How often do you need to change them? So much more down to earth.
We mean rowing. Yeah. Well, hi, Charles. I'm hoping to see you soon, my friend. Well, the whole idea is this is printed. The hands that you've seen there, they cost around $100. With the electronics, with everything, to print the hand, tens of dollars. It's really low cost. So the idea is that you can build something that if it breaks, it costs you nothing to replace it. If you go look at one of those professional, which are amazing, by the way, in the market, the professional, prosthetic hands that cost tens of thousands of dollars. Each motor there costs more than the entire hand. So I can produce 3 or 4 hands in the cost of one motor there. So yeah, if it breaks, if it falls apart, you just print new one, and all you need is a 3D printer and maybe someone with a little bit knowledge of technology, and you just put it together. And children, they play, and they tend to play. You want these children to be active like any other children, and they play in the dust, they play in the water, they play everywhere. So if it breaks, you just print new part, replace it, and it's very fast, very intuitive. Do it yourself, like IKEA. We give you also the brochure, yeah.
We hope it's easier than an IKEA thing that you actually need to put together.
Yeah.
Sure. Thank you very much, Alon. Thank you for being with us.
It's a pleasure.
Thank you.
Nice to see you. Bye-bye, Alon. Bye. See you.
Bye-bye.
See you soon. Thank you.
Merci, Elsie. Bravo pour cet accent anglais si fluide.